The first Trijet airliner in service. The first aircraft with triple slotted flaps. The first transport with an APU. The first and only airliner with a nose gear brake. The first aircraft with perforated inlet liners for fan noise reduction. The first big jet designed for sub 5,000 foot runways. There is much 707 and 720 DNA in here, but the 727 clearly was next level through its many firsts and quirky innovations. Let's take a closer look and try and answer questions like, what was all the magnesium on the bill of materials for? Just how many yaw dampers is enough yaw dampers on a jet like this? Why were the pilots of this aircraft mechanically prevented from using all its flap settings? And following what moment of the flight test campaign did test pilot Lou Wallach Jr. say, let's not do that again? But before all that, let me introduce you to an absolute gem that is going to help us illustrate much of what follows. This very cool looking 727 is a 200 series, technically a 727-269, 69 being the Boeing customer code for Kuwait Airways, to whom this airplane was delivered in the summer of 1980. So she's a relatively late example. Production of the 727 ended in 1984, and she's currently being looked after and kept in this stunning condition by Mr. Mark Gregory of Air Salvage International, to whom I am mighty grateful for the opportunity to crawl all over what is, I think, the best of many cool aeroplanes in his custody. The three hush-kitted JT8Ds are the final model made for the 727 by Pratt & Whitney, the -17 Romeo series. As we climb on board via the 72's famous/infamous, rather neatly integrated rear air stair, a quick look around reveals that the mint exterior of this aeroplane is rather well matched by its absolutely stunning interior. And, well, would you just look at that? The aeroplane has had a rather colourful history. It's worn 4 different registrations over the last 4.5 decades, had several careful owners. Little old lady, flew it to the church on Sundays, etc. If you'd like to delve a little deeper into Oscar Hotel's interesting past, there is an Airliner World article from a couple of years ago by Martin Needham. That could be a useful starting point. So much to admire here, from the lovely analog flight deck to the extraordinary furnishings. Selecting the size and the range can make or break an airliner. Superbly engineered aircraft can become commercial failures if those numbers are not quite right for the market. Think Hawker Siddeley Trident 1. Think Dassault Mercure. Here is what the early jet era looked like in terms of passenger payload and range. The mighty 707, when it wasn't being dug out of the snow in Chicago by Joe Petroni, could carry just over 100 passengers from JFK as far as Paris-Le Bourget, but was also serving short-haul pairs like JFK Miami with up to 140 passengers on board. Vying for the bottom left corner of the payload range space, featuring city pairs like Heathrow Paris, Detroit Columbus and Albuquerque Dallas, were early twin jets like the Sud Aviation Caravelle and the DC-9, and the aforementioned technologically super clever but unfortunately short-ranged Hawker Siddeley Trident, which was incidentally the first Trijet transport to fly. Boeing decided to target the fresh air in between with a concept that would become the 727-100, which flew for the first time on the 9th of February 1963 with Lew Wallack Jr. at the controls. More on him in a bit. Nearly 600 of these would be sold in the coming years. A version stretched by 20 feet, the Dash 200, would follow 4 years later and would become a roaring success, bringing the total tally to over 1,800 727s. There were three major party tricks that the 727 was meant to achieve, beyond what is obvious from this chart. One, it had to be fast. Economical cruise around Mach 0.8, but headroom for up to 0.9. Two, it had to be able to operate a long way away from suitable diversion airports. Think Chicago San Juan. And three, it had to get into and out of LaGuardia's then 4,860-foot runway. And these often competing constraints asked some mighty big questions of the propulsion and aerodynamics engineers in Renton. There is an interesting insight in an AIAA paper by the head of the 727 program, Jack Steiner, who recalls United Airlines having wanted a 30-degree leading-edge sweep on the wings of the aircraft, while all Boeing fast transports to date had a 35-degree sweep. In the end, the 32.5-degree sweep of the wings of the 727, generally quoted as 32 degrees, is the result of them meeting halfway. It's all really odd from a 2020's perspective. Why would an airline have a view on geometrical design variables rather than just on the actual capabilities of the aeroplane, letting the manufacturer figure out how to best achieve those? Aside from the leading edge sweep, the starting point of the design process was the wing of the Boeing 720 short-haul quad jet, which had a rather sporty design Mach number of 0.83 at a cruise lift coefficient of 0.4. And some 2 years and 35 alternative design studies later, what emerged was a clean wing with slightly less speed capability than the 720, but a better lift-to-drag ratio. The big outstanding question was, how big would this wing have to be? In other words, what would the wing loading be? Efficient fast cruise and low weight demands a highly loaded wing. But a high wing loading generally means high approach speed, and if you want to get into a 4,860-foot runway, then you will need a low approach speed. Also, in the 60s, lower approach speeds meant more operational flexibility and safety in terms of low cloud operations. Boeing estimated that if you broke out of a 100-foot cloud base at a ground speed of 100 knots, you could still correct a lateral position error of 100 feet. But at an approach speed of 140 knots, this maximum error was down to 40 feet, and the pilot of an aircraft flying a 160-knot approach only had about a 20-foot error margin in terms of lateral corrections before touchdown. To meet the competing objectives of efficient cruise and short-field capability, Boeing set to work on a high-lift system capable of more than doubling the lift that the clean wing generated. They broke out the yellow Dash 80 prototype quadjet built in the early 50s as a jet propulsion test bed to lay the groundwork for the 707. And they used it to test a variety of high-lift system designs. Over a 5-phase, 20-month program, they looked at a range of options, including some rather wild solutions like flaps blown by bleed air from the engines. This was the flavour of the month then. At the same time, over in Britain, hunting aircraft were building a blown flap flying demonstrator. The somewhat ungainly but very interesting Model 126, featuring these bundles of bleed air ducts providing high pressure flow through a thin letterbox outlet in each trailing edge flap. Boeing even looked at a leading edge version of this towards the end of the test program. According to a Flight International report from 1963, 41 Boeing engineers were engaged solely in the laying out of different high lift configurations.
when they stepped back from their 41 drawing boards, what emerged possibly remains to this day the most complex high-lift system ever conceived. A mechanical marvel that, despite its large moving part count, would go on to provide many decades of generally reliable service on the 727 fleet. They did stop short of blown flaps in the end, but the final design featured a triple slotted Fowler configuration, the first such system in the world. Its work would be supported by 3 leading-edge inboard Kruger flaps and 4 outboard slats. And the result was some rather excellent low-speed performance. Here's the book value of the 1G stall speed of the clean wing, ranging from 125 knots calibrated at 50 tons gross weight to 184 knots calibrated near the maximum takeoff weight. This data is for the later, heavier -200 variant. Then a range of options for takeoff and initial approach, with 25 degrees of flap taking roughly 50 knots off the clean values, actually nearly 60 at maximum takeoff weight. Things get rather interesting when we get to the landing stages of the flap system, 30 and 40 degrees. The final 40-degree stage gains us, on paper, 2 to 3 knots of stall speed and thus approach speed at lower weights, compared to flaps 30. But this advantage disappears at the top end of the weight scale. In fact, we might get slightly better lift performance from the 30-degree stage near the maximum landing weight. Making some assumptions here, notably that the quoted book value of the stall speed is the same as the real aerodynamic value of the 1G stall speed, we can turn this picture into maximum lift coefficient estimates, or perhaps take them as lift coefficient at the stall to be more precise. 40 degrees of flap give us a pretty eye-watering maximum CL of nearly 2.9, at least in theory. But there are several practical design considerations here that might beg this back. 1. The approach speed must be greater than the best lift to drag speed. In other words, we must be on the right-hand side of the drag curve on the approach. This is because the low speed side of the drag curve is speed unstable. So anything that may slow the aircraft down would increase the drag and thus slow it down further. Not ideal when we are only 30% above the 1G stall speed to begin with. 2. Pitch stability. CAR4B, the certification basis for the 727, prescribes that the stick force curve shall have a stable slope at all speeds between 10% and 80% above stall up to the maximum landing weight. 3. The approach attitude of the aircraft at all weights should be such that the pilot has a good view of the runway, and of course the tail skid does not meet the tarmac before the main landing gear does. This required attitude translates into an alpha of about 5 degrees on the 727. 4. The go-around constraint. If the approach speed flap setting is too draggy, the climb gradient after a go-around may not meet the regulatory minimum requirement for obstacle clearance. 5. Stall characteristics. What was the handling like at the stall with the various stages? The desire for a more gradual, benign stall was part of the reason for having the multiple slots in the Fowler system. Boeing found that slots meant more gradual loss of lift at the stall. The leading edge Kruger flaps also play a significant role in determining the quality of the stall, and they can also raise the CL max significantly. But, and here we run up against constraint number 3, they can push the alpha corresponding to CL max to unacceptably high values. 6. The clean wing has to be efficient at high speed. This typically means a thin leading edge, and in the case of the 727, a rapidly thinning leading edge as we move outboard, which means that there isn't much chord-wise real estate on the outboard section for slats. In other words, their chord length is limited by the leading edge radius. And outboard slats were needed to ensure that an outboard first stall does not cause a potentially dangerous pitch-up tendency at the stall, more on which later. Leading edge Krugers, like we have on the inboard section, were not found to be satisfactory for this job, which was unwelcome news because slats tend to have more awkward deployment mechanisms. Once again, there are no free lunches in engineering. Success is about finding the best trade-offs nestling in the middle of a spaghetti junction of constraints. And if you cannot pacify all constraints geometrically, you have to do it via operational limitations. And this is the case with the 727's flap system. Despite marginally better CR max, at least at lower weights, flaps 30 ended up designated as the normal landing setting, with 40 degrees only to be used under adverse conditions: slippery runway, runway length of 7,000 feet or less, braking action less than good. In fact, after some early approach accidents at flaps 40, some operators ended up locking out the final stage. The whole thing is really a cautionary tale for the aircraft design student. Taking some 2D multi-element airfoil CR max and plugging it into a landing performance model is perhaps a good way of obtaining an order of magnitude guess. But reality might be a lot more 3D, especially on a highly swept wing, and it will almost certainly be constrained from all directions. The leading edge Kruger flaps and the trailing edge flaps are magnesium castings, an alloy called AZ92 containing 89% magnesium, 9% aluminium and 2% zinc. Magnesium is less common today as a structural material, but it makes perfect sense here since its density is about 40% less than that of aluminium. Its use makes sense where the shape and thus volume of the part is dictated by aerodynamic constraints and more stiffness is required than can be achieved by a thinner aluminium shell structure. A similar effect can be achieved with aluminium honeycomb structures, and these can indeed be found in a few places around the wing, such as the flight and ground spoilers. The inboard Kruger flaps are of the bullnose variety. The bullnose fairing is retractable, and it is mechanically linked to the flap deployment mechanism. The hinge of the bullnose disappears inside the clean wing on retraction. The slats on the outboard section of the leading edge are deployed via simple linear hydraulic actuators. It is interesting to compare this setup with what Boeing would go on to do later on the 747, which has inboard Krugers, similar to those on the 727, but instead of slats, it has variable camber outboard Kruger flaps, as seen on this Virgin 747-400. Back on the 727, the trailing edge in between the two segments of the triple slotted Fowler flaps also features a high-speed aileron to augment the authority of the low-speed one outboard. This would subsequently become part of the Boeing house style, if you like, with their airliners featuring a high-speed flaperon between the two flap segments, as can be seen here in the thrust gate of a 787 and on the 777-9 as well. Unlike on Airbus aircraft, for example, which have directly adjacent flap segments. Let's begin with the gorgeous SWAT Tail of the 727, featuring 3 Pratt & Whitney JT8D low bypass turbofans developed specifically for the 727. So why, for the first time in the jet age of transport, 3 engines? Some of Boeing's early studies actually looked at a sort of mini 720 quad jet. But in a desire to cut costs, they ended up looking at concepts with fewer engines. This basically sort of meant 2 at the time, because multi-engine props tended to have an even number of engines. Once again, the customers made their feelings on the subject known, American Airlines were sort of agnostic, but motivated by overwater routes and all-weather field performance constraints, Pan Am and Eastern wanted more than 2 engines. Boeing wanted fewer than 4. There was limited need here for higher mathematics to work out that they would need to go with 3. The same way de Havilland went at the same time on the other side of the Atlantic with the aircraft we now know as the Hawker Siddeley Trident. But the decision to build one of the first 2 Trijet transports in the world opened a whole new can of worms. Where do you put 3 engines? 2 slung under the wings, 707 style, and the third one on the tail. A few years later, the Lockheed 1011, for instance, would adopt this option, but Boeing were leaning very heavily on the high lift system on the 727 for eking out every bit of CR max for landing performance reasons, and the wing also having to accommodate engines would have made life very difficult for the designers of both the leading and trailing edge devices. Boeing would later go on to interrupt the Kruger flaps on some aircraft, twice in fact on the 747, but the additional mechanical complexity and aerodynamic complexity was considered too problematic on the 727. Later 737s with wing-mounted engines are a good illustration of these issues. You have to account for the pendulum-like oscillatory modes of the engines. Look at how, because of this, the Krugers had to have an additional spring-loaded hinge mechanism and a rubber seal on the 737-300. So, engines numbers 1 and 3 went on each side of the tail. But this still left 2 options open for number 2. On top of the fuselage with a straight duct, or buried inside the fuselage and fed by an S-shaped air intake duct. Jumping forward in time again for a moment, the Lockheed 1011 is once more an interesting case study because obviously Lockheed's engineers were faced with the same dilemma on their number 2. In the end, they opted for the S-duct option, and in an SAE transactions paper published in 1969, they laid out the reasons quite clearly. Pressure recoveries for the 2 options were found, perhaps counterintuitively, to be similar, as were crosswind-induced pressure distortions. They found lower total aft fuselage drag with the S-duct, lower structural weight, the engine being closer to the ground meant easier maintenance, and a lower operating cost over the straight duct. One could think of other advantages too. For example, better handling as a result of having the middle engine closer to the height of the center of gravity. It all makes sense, all solid arguments. Except that McDonnell Douglas's engineers working at the same time on the similar sized, similarly configured DC-10 Trijet, presumably equally confidently and on equally solid ground, went exactly the opposite way, with a high-mounted engine fed by a straight duct. Of course, what is always troublesome with S-ducted engines is that the pressure recovery seen by the fan face of the buried engine is always distorted in the plane of the S. And this is bound to introduce a harmonic load on the fan blades and thus a source of fatigue. In any case, having no doubt weighed all these pros and cons, Boeing went with the S-duct option on the 727, as did de Havilland with the Trident, Tupolev with the Tu-154, Yakovlev with the Yak-40. Not much in production by way of Trijets today, but the last remaining such design, the Dassault Falcon family, also features the 727 style S-duct design. This seems to have vindicated Boeing's decision. Now, there is one more twist in the tail of the propulsion system in the shape of a rather unusual upgrade Boeing were offering with the Dash 200 Advanced variant, a set of 6 Aerojet 15 kilo Sierra 1000 thrust augmentation units. These were rocket motors capable of producing 1,000 pounds of thrust each for 15 seconds. This sounds exotic, but was tried and tested technology. Aerojet General Corporation made about 250,000 of these units, and they had flown successfully, helping bombers lift heavy payloads during the Korean War. So, what was the point of installing these devices on the 727? The answer is hot and high field performance. Specifically the case when the maximum payload the aircraft could lift from a high elevation runway was limited by the engine failure at takeoff constraint. Specifically, the failure of the critical engine at or past the decision speed V1. Let's take the case of Mexico City Airport at an elevation of over 7,000 feet. In these conditions, a flat 15 takeoff would be prescribed up to just over 74 tons takeoff weight. Then a 5 degrees of flap takeoff would be prescribed up to 76 tons. At this point, however, in the engine failure at takeoff case, we're approaching 15,000 feet of field length, which is not ideal if, for example, you have less than 13,000 to play with, like at Mexico City. And this is where the rocket assist six-pack comes in. In case of an engine failure, they can be fired to give us substantially more payload capability. In the case of Mexico City, over 4 additional tons of payload can be lifted in this limiting case. In the end, Mexicana's 12-200 advanced jets remained the only 727s equipped with this cool RATO system, and later versions of the JT-8D featured an automatic power reserve system, which boosted the maximum thrust on the 2 good engines if one failed, thus achieving a similar effect and obviating the rockets. So the world was left with a dozen 727s with emergency rocket power, plus a team of test engineers who no doubt had their time of their lives flight testing this thing. Let us now return to the rather magnificently swept tail of the 727 for a moment. Why is it the size it is? The answer is, of course, as small as Boeing felt they could get away with. Obviously, minimal drag, weight, cost and height are all desirable here. If the 727 was being designed today, the engineers' minds might first be going to paragraph 149 in 14 CFR 25, namely to VMCG, or the minimum control speed on the ground, which quite often ends up driving the tail size. But the 727 was designed before 14 CFR 25 149, and minimum control speed on the ground wasn't a thing then. VMCA, however, was in CAR 4B, the airworthiness standard on the basis of which the 727 was certified. Here is what 4B133 has to say on the subject of VMCA. Well, VMC as it was called then. A minimum speed shall be determined under the conditions specified in this paragraph, so that when the critical engine is suddenly made inoperative, at that speed it shall be possible to recover control of the airplane with the engine still inoperative and maintain it in straight flight at that speed, either with zero yaw or, at the option of the applicant, with an angle of bank not in excess of 5 degrees. Such speed shall not exceed 1.2 times the stall speed. The tail mounting of the engines was good news here for the control team on the 727, with engines number 1 and 3 quite close to the center line, and therefore the critical engine inoperative yawing moment being quite low. It is likely that this constraint was not particularly restrictive, though perhaps it was the reason for the addition of a row of vortex generators upstream of the rudders, designed to ensure rudder authority at sub 1.2 times stall and big side slip angles. But I'm speculating here. So what did drive the fin size? The answer is likely to be the Dutch roll constraint. And let me insert a little sidebar here on why this can be quite tricky. On a basic level, Dutch roll is a damped oscillatory motion consisting of a mix of side slip, yaw and roll. From the cabin, you see Dutch roll as the wingtip drawing an elliptical cycloid over the horizon. The greater the roll component, the less eccentric the ellipse. From the flight deck, it looks like the nose drawing a figure of 8 over the horizon. Generally, Dutch roll is not a safety issue, nor is it especially inconvenient if it is convergent and well damped. There are basically 4 ways of increasing the damping of the Dutch roll. Increasing roll stability, increasing roll damping, this is the roll subsidence mode, and increasing yaw stability and yaw damping. Check out Warren Phillips's magnificent doorstop of a book for a rigorous mathematical treatment of this stuff. Now, all this seems to demand a larger tail fin size. After all, more tail area would increase yaw stability, it would increase yaw damping, it would even increase roll subsidence to a certain extent. But aside from the added real estate on the tail, also increasing weight and pressure drag, there is another catch. The increased yaw stability has a destabilizing effect on the spiral mode of the aeroplane. So you can't go too far tail sizing your way out of Dutch roll, because you might end up engineering yourself into spiral divergence. There are alternatives. You could have a smaller fin forward of the center of gravity, which would decrease your stability but would increase your damping. However, that would again add a massive weight penalty and would look extremely silly. A more sensible alternative is to add long flat fins under the tail, which don't generate much lift in side slips, so won't increase your stability, but they do increase roll subsidence and they do increase your damping, so will also increase Dutch roll damping. There aren't any such fins on the 727, probably mainly because they would have eaten into the maximum deck angle on landing. There is, nevertheless, reason to suspect that Boeing were concerned about Dutch roll on the 727, and here's why. If you cannot engineer a naturally strongly damped Dutch roll, and due to the aforementioned competing trade-offs, this is a common problem, there is a control system solution, and that is to have a yaw damper. This is an electronic system that generates a damping rudder input, in addition to whatever rudder deflection the pilot already has on, proportional to the yaw rate, designed to counter the Dutch roll. Now, not only does the 727 have an electronic yaw damper, but the system is active whenever the aircraft is powered up, and it consists of 2 entirely independent yaw damper subsystems. This is a bit unusual. They are independent to the point of each having its own rudder. I don't know if the 727 had a poorly damped or even divergent Dutch roll, but this sure looks like serious belts and braces. Moreover, in case the aircraft is dispatched with in-op yaw dampers, strict altitude and speed limits were mandated. Dutch roll is generally a bigger issue at high altitude because the damping is naturally lower at a lower ambient density. For additional colour, it is perhaps also worth mentioning that Boeing's engineers may have had a particular accident on their minds, which occurred at about the time the 727's yaw damper was being designed, when a 707 crashed on a training flight after the crew lost control during a Dutch roll recovery exercise. And another small footnote, check out Design Deep Dive 1 to see, through a real-life, in-the-air demonstration, what a difference a yaw damper makes. In that case on a Saab 340, an aeroplane that, unlike the 727, does have ventral fins and does allow the pilots to turn off the yaw damper thus allowing some with and without comparisons. While Boeing were flight testing the 727, another T-tailed airliner was undergoing flight testing, the British Aircraft Corporation 111. On the 22nd of October 1963, BAC 111 Gulf Alpha Sierra Hotel Gulf was undergoing stall testing 15,000 feet above Wiltshire. On the fifth test of the day, with flaps at 8 degrees, the crew lost control of the aircraft, which reached a massive angle of attack of 40 degrees at one point, before descending rapidly in a flat attitude, smashing into the ground about 90 seconds later. All 7 crew were killed. The culprit was found to be a strong pitch-up tendency at the stall, caused by the loss of elevator authority, as the separated turbulent flow over the wing enveloped the tailplane. Every pilot wishes for an aeroplane that naturally pitches down at the stall G-brake, and so did the 111 at first, at about 15 to 19 degrees, but then in the sudden sharp rise in alpha, following the loss of lift in the stall, beyond about 25 degrees, a strong, unrecoverable pitch-up tendency was apparent, causing what is known as deep stall. It was perhaps at least partly this incident that prompted Boeing and the FAA to sweep the central gravity range of the 727 with a program of about 700 stall tests, including flaps down, spoilers up configurations, typical of the approach. And it was at one of these test points that test pilot Lew Wallach and his crew found themselves in a near deep stall situation. We know this from a biography of the great man written by his daughter Rebecca, who describes how Mr. Wallach managed to somehow recover by applying full power, closing the spoilers and applying full nose down elevator, somehow recovering from a potentially fatal incipient flat spin. In the ensuing silence on the flight deck, uttering the words, "Let's not do that again." Another flight test legend, Di Davis, him of handling the big jets fame, chief test pilot of the UK Civil Aviation Authority, recalls Wallach telling him, "There's not a hope in hell of you accepting this aeroplane. We have had 2 of the most hairy beep beep stalls you have seen in your whole life." By not accepting it, he was referring to CAA certification of the aeroplane, which Dan Air wanted to operate in the UK and needed Davis's blessing to do so. Davis nonetheless proceeded to fly some stall tests on the 727. As he recounts in an interview given in the 90s to the Royal Aeronautical Society, he found the aeroplane docile and the stall nice and safe at forward centres of gravity, but quite desperately unstable at aft CG, approach configuration stalls, where he found that the aeroplane pitched up, and had he not recovered at there be dragons there alpha limit specified by Boeing, it would no doubt have deep stalled on him. This left him stunned that the FAA would accept the aeroplane. Boeing duly modified the design by fitting a stick pusher, the best stick pusher I've ever flown, as Davis recalls, which would protect the edge of the flight envelope from accidental visits by unwary pilots. The pusher would, however, only be fitted to UK registered 727s. All others only had a stall warning stick shaker, which would thus have Davis's stamp of approval, who, by the way, noted that the 727's handling was a gift in all other ways, one of the nicest aeroplanes he'd ever flown. Also, he had no quarrels with the handling of the later longer -200 model. Now, a -200 would end up lost in an accident about a decade later on a repositioning flight, Northwest Orient 6231, when the crew were unable to recover from what could, in some sense, be interpreted as a deep stall. But this was the result of the crew desperately trying to correct what they believed to be an overspeed situation, even misreading the stick shaker as Mark Buffett. And these actions were the very opposite of stall recovery. Probably even not doing anything would have been sufficient for recovery. Would a stick pusher have made a difference here? We will never know. It is particularly hard to tell, as the root cause of the accident was a heavily degraded air data system. The crew had flown into icing conditions with the pitot heat off. The 727 has two main gears with two wheels each, featuring a short, thick shock strut. The 737 wasn't the first Boeing airliner to feature a somewhat short undercarriage to facilitate freight loading. Between the wheels sits a little gravel deflector panel designed to protect the brake lines. There is a much thinner side strut, which has two elements. The lower cylindrical element, with the tire inflation card conveniently strapped to it, hinges off an upper steel forged part through a universal joint, which is where it all folds on retraction into the wheel well integrated into the fuselage. The upper part is, in turn, hinged on its attachment to the primary structure of the aeroplane. The solid-looking part here is a forged aluminium extension of the rear spar. Incidentally, the rest of the landing gear primary structure is made of high tensile steel. The downlock and its spring are also attached to the upper segment of the side strut. Looking at the main gear from behind, we can see the drag brace attached to the trunnion link just about visible at the top. This is the sacrificial part of the gear. That shear pin there is supposed to fail in a hard landing, thus protecting the primary structure. But the funkiest feature of the whole assembly is this little curved I-beam operating the gear door. The way it is having to somewhat awkwardly snake around the drag strut shows just how hard the gear retraction is to choreograph. By the way, unlike on later single-aisle Boeings, where the outside wheel on each main landing gear forms part of the outer surface of the airframe when retracted, on all 727 models, the doors fully cover the main landing gear well when the gear is retracted. Let us now pay the nose gear a visit, where things get more interesting still. At first glance, nothing unusual. Once again, a short shock strut and a fairly conventional steering mechanism with two prominent actuator cylinders protruding forward above the taxi light, both pin-jointed to a steering collar. But let's have another look from the front. The very astute viewer will have spotted a brake assembly. That's right, the 727 has nose gear brakes. This is a super rare feature, the 727 being probably the only airliner in history to feature a braked nose gear. Let me know if you know otherwise. In fact, there aren't many aircraft out there at all with brakes on the nose gear. Some versions of the Messerschmitt Me-262 and the Saab Gripen, designed to operate off very wet runways and even roads if need be, being the only other examples I can think of, aside perhaps from some one-off experimental oddities. Now, while aircraft engineers love a bit of redundancy, there are good reasons not to have brakes on the nose gear, mainly to do with them not really earning their keep in terms of the added weight and complexity. And sure enough, the nose gear brakes quietly disappeared off the 727 during its production run, and some that had been fitted got deactivated and removed. Here is a Dash 100 model with bare mounting points and fresh air where the brake assembly would have been. Nevertheless, there was some neat compact engineering on these nose gear brakes, with a hydraulic line running through the shock strut of the nose gear. A final noteworthy feature of the nose gear, there are deep chines molded into the sidewalls of the tyre. This is to do with wet weather field performance. A more conventionally contoured tyre might kick standing water straight into the intakes of the two side engines on a runway with standing water. This sort of chine can be seen on other aircraft of the era with tail-mounted engines such as the Vickers VC-10. A gear-related feature of the 727 is the retractable tail skid, designed to protect the airframe from damage caused by tail strikes on over-rotated takeoffs. There is a sacrificial crushable honeycomb cartridge supporting the skid, designed to absorb the energy of the impact. The skid is retractable, and if for whatever reason it does not retract, a warning light comes on the flight engineer's panel. This is because, in this situation, the crew must account for the fuel burn penalty associated with the additional parasitic drag of the skin hanging into, and possibly beyond, the boundary layer around the aft fuselage. The manual actually recommends cutting the range estimate by 10% and adding 25% to the climb time estimate. Seems like a lot. A similar skid can be found on the longer 737s as well, the Dash 400, 800, 900, and all but the shortest of the Maxes. And while we are under the tail, let's spare a thought for the aft air stair. This wasn't all that rare at the time. Here is the one on the BAC 111. But of course the one on the 727 is more notorious than most, thanks to Mr. D.B. Cooper having exited a 727-100 mid-air one November night in 1971 over Washington, parachuting off the air stair with the ransom money he had obtained through hijacking the aircraft, never to be seen again. Nor was a similar stunt ever seen again because of a small change that was made to the design of a 727, a small vein, inevitably named the Cooper vein, that mechanically prevented the door from opening when air was flowing over it. A simple, robust, cheap and elegant solution. Visually, much of the DNA of the 727 still survives in Boeing's modern-day single-aisle jets. But where are we in terms of performance? I find it interesting as a measure of progress to compare over time aeroplanes with the same operating empty weight. Empty meaning not including the payload and any usable fuel. The JT8D-7 powered 727-200 had an operating empty weight of just over 45 tons. Boeing have an approximately 45-ton operating empty weight single-aisle jet today too. It is the 737 MAX 8. It lifts 15% more payload than the 727 did, and here comes the important bit, it takes it twice as far. That is what we get from almost exactly half a century of engineering progress. Now this isn't a perfect comparison because the 727 was actually faster than even the modern day 737s. But it's nonetheless true that the same weight of structure in a modern 737 carries the equivalent of about 30 more passengers, plus enough fuel for going 1,300 nautical miles further. That's a London to Istanbul or Seattle to Kansas City remaining in the tanks of the 737 after the 727 would have had to land. So we've come a long way in the 50 years that have passed between the 7.2 and its modern day closest relative, the MAX 8, metaphorically and literally. We are in the sunset decades of the operational life of the 727, with a few freighter converted examples still around and others converted for special operations, like, for example, flying 0G parabolas, November 794 Alpha Juliet, also known as G-Force 1, can count Stephen Hawking amongst its past list of people who got to experience weightlessness on board. In the UK, 2XL Aviation fly two 727-200s including the last example to come off the line back in 1984. They operate as an oil spill response facility, airborne platforms capable of spraying an oil dispersant onto the sea surface. But most importantly, some of the clever engineering innovations of the 727 and what we learned from them in half a century operations live on, woven into the engineering fabric of modern airliners.